Hello, everyone. Welcome to the third lecture of our Introduction to Modular Forms. So today, finally, we are going to start our discussion on modular forms. So in the previous lectures, we covered the prerequisites needed, such as we covered some fundamentals of group theory, that is, the definitions of group action, orbit of a group action, and so on and so forth. And in the second one, we covered some preliminaries of complex analysis that we'll be needing throughout the classes. Okay, so finally, we are starting modular forms. Modular forms. Now, before I give the rigorous definition of what a modular form is, I want to begin with some motivation. Because if I just throw out the definition first, then like without any motivation, like it may not be clear to everyone that why do we need such a construction. So before defining what a modular form is, we are gonna build up some intuition or some motivation. Okay. So first of all, the term modular means moduli space of complex elliptic curves. So historically, the term modular has been used to mean moduli spaces of complex elliptic curves. So I'm going to define what these things are. So basically, a complex elliptic curve is a curve of this form: y square equals to x cubed plus ax plus b, where a and b are complex numbers. Okay, so this is a complex elliptic curve. Also, this has to satisfy some conditions. So I'm not gonna define like like which conditions we have to satisfy, but yeah, you get the idea. So now, what is a moduli space of complex elliptic curve? So before that, we need to define something. Let's say I think I defined what a lattice is, right? So nevertheless, I'm going to define it again. So definition of a lattice. So a lattice is basically a discrete subgroup of the complex plane. So so let's say this. Sorry. So let's say this is a subset of C, and we are assuming this is a subgroup as well. So we shall call this is a lattice if all the elements are of this form: m omega 1 plus n omega 2, where n and m are integers, and also omega 1 and omega 2 are complex numbers such that their ratio is not a real number. Is not a real number. Okay. So sometimes we shall say that this lattice is generated by omega 1 and omega 2. Okay. So this is a lattice, and we shall call two lattices homothetic if a condition is satisfied. So I'm going to define that condition. So let's say this is gamma, right, or lambda. This is capital lambda. So this is so capital lambda and capital lambda prime are two lattices, and we shall say lambda and lambda prime are homothetic if lambda prime is equal to some lambda times lambda. So what is this small lambda? Small lambda is a non-zero complex number. And this is basically the set of all elements of this form. So basically, from the lattice capital lambda, I take all the points and I multiply all the points by a non-zero complex number lambda. So then the set we get, if that set is equal to the other lattice, we say that these two lattices are homothetic. So visually speaking, let's say my lattice is the lattice of all the Gaussian integers, that is all the integers. And so that lattice is generated by 1 and I. Okay. So in the lattice of Gaussian integers, all the elements are of this form a plus bi, where a and b are integers. Okay. Okay, so this is the lattice of all the Gaussian integers, and all the elements are of the form a plus bi, where a and b are integers. And let's say I have another lattice that is like this. So that lattice is suppose generated by this one, this complex number and this complex number. Suppose this is 1 plus I, and this is negative 1 plus I. Okay, so we get another lattice that is generated by these two elements, right? So what are the elements of that lattice? I guess this one, this, yeah. Yeah, so you get the idea, right? So can you see that these two lattices are homothetic? Because you just take the lattice of Gaussian integers and you multiply it by, you, do we multiply it by I or 1 plus I? Because 1 plus I times I is equal to negative 1 plus I, right? So this lattice is generated by 1 and I, and if I multiply 1 and I by this number 1 plus I, then I get this one and this one. So these two generates the lattice. Yeah. So basically, if I have a lattice, and if I sort of stretch the lattice and rotate it, then I get another one. So and those two lattices are called homothetic. Okay. And
doesn't it mean like you can get omega 1 and omega 2 by somehow like multiplying something? So if you can get omega 1 and omega 2, that means the lattice generated by omega 1 and omega 2, like that lattice is
right. So you're basically saying that the lattice generated by omega 1 and omega 2, that is homothetic with the lattice generated by, let's say, lambda omega 1 and lambda omega 2. Yeah. And when two lattices are homothetic, we denote it like this. Okay, and in LaTeX, this is probably backslash sim ec, probably. Okay.
So when two lattices are not
Oh, that's a very good question. So let's say I have a lattice that is generated by 1 and this complex number. And I have another lattice that, let's say, that is generated by 1 and this complex number. So if I like rotate and stretch this parallelogram right here, I can get this one. All right. Yeah, we can make a linear transformation, but we are not talking about linear transformations here. So we are calling two lattices are homothetic if we multiply all the points of one lattice by a non-zero complex number, and we get the other lattice. Then we shall call the two lattices are homothetic. Okay, and when two lattices are homothetic, we shall denote it like this. So yeah, and suppose curly L is the set of all lattices on C, then I can form this. So this is basically all the equivalence classes of lattices under the homothety relation. Okay, all right. And there's this theorem in the theory of elliptic curves that every lattice is so if I have a lattice on the complex plane, that lattice corresponds to an elliptic curve. Okay, so if I have a lattice here, this corresponds to a complex elliptic curve. So this corresponds to an elliptic curve, and uh, elliptic curves have a group structure, an abelian group structure, and basically if this lambda corresponds to an elliptic curve E, then the abelian group of this elliptic curve is isomorphic to this quotient group. So you can see that a lattice is a subgroup of C, right? Because all the elements are of the form A omega 1 plus B omega 2, where A and B are integers. All right. So yeah, so an elliptic curve that is generated from a lattice, the abelian group of that elliptic curve is isomorphic to C quotient lambda. Okay. And yeah, also the converse is true as well. Like if I have an elliptic curve, so there must be if I have an elliptic curve, so there must be a lattice in the complex plane that lattice generates the elliptic curve. Okay. So yeah. So sorry. So this correspondence is goes both ways. Okay. So and we can talk about the isomorphism classes of the elliptic curves, right? Because elliptic curves are abelian groups, as I said. And let's say lambda 1 is a lattice that corresponds to an elliptic curve E1, and lambda 2 is a lattice that corresponds to E2. Okay. Then then we have a theorem that is E1 and E2 are isomorphic. So remember, E1 and E2 are elliptic curves, so they can be considered as abelian groups. So these yeah. So these two elliptic curves are isomorphic as abelian groups if and only if the two lattices are homothetic. Okay. So if we want to study isomorphism classes of elliptic curves, it suffices to study this the set of all the lattices over C and modded out by the equivalence relation of homothety. So if we want to study the isomorphism classes of elliptic curves, it's sufficient if we just work on this. Okay. All right. Yeah. So if we want to study this set, if we want to study this set, so it is natural to consider functions from this set to complex numbers. So we want to study this set, so it is natural to consider functions like this. Okay. For instance, if I want to study a vector space, so it's natural to consider all the linear maps from the vector space to the field, right? So the set of all those linear maps from the vector space to the field is called the dual space. So that works as a motivating example here. So we can consider functions like this, and yeah, and all of these functions basically give rise to another function. Because here the elements of this set are equivalence classes, right? So the elements are equivalence classes, and all the members of this equivalence class is mapped to the same element here. So what property does G have? G have the property that G of lambda is equal to G of capital lambda for all non-zero complex number. Okay. So we can interpret this as like G is sort of invariant under multiplication by a complex number. Okay. But turns out studying these kind of functions is a very restrictive situation. So in order to find such a function, so what we can do is that maybe we can find like two functions that are like, so let's say f and g. So if I find two functions that do not have this property, like f of lambda is not f of lambda, rather there are some fudge factor here. And if G also has this property that G of small lambda times capital lambda is not G of lambda, sorry, it should be G of f of capital lambda. So suppose f and G do not have this property here. So there are some fudge factors here. And if these two factors are the same, we can consider f over G. Then f over G has our desired property. Okay. So what can we like require in place of this little fudge factor? So one very natural idea is to consider homogeneous functions. Okay. So I'm going to now define what a homogeneous function is. Notice all these functions we are considering, they are from the set of all the lattices to the set of complex number. Okay. Definition: a function f from L to C is called homogeneous. So I'm going to write something here. So I'm going to leave it blank for now. If f of lambda times lambda is equal to lambda to the power k f of lambda. And this has to be true for all non-zero complex number. So, and if this is true, we call the function homogeneous of weight k. Okay, so the motivation is, I think, clear because like if we have a homogeneous polynomial, so let's say a homogeneous polynomial is a polynomial whose all the terms have the same degree. Suppose x square y plus y cube. This is a homogeneous polynomial. And if this is, let's say, p of x comma y, then p of tx comma ty is equal to t to the power 3. 3 is the degree p of x comma y, right? So yeah, keeping this motivating example in mind, we define a homogeneous function of weight k like this. But turns out we have another problem here, that is constructing such functions is not easy at all. So in fact, like so if you want to like construct such a function, let's say a function that has this property. So one example might be this. So I define f of lambda to be the sum of omega to the power k, where omega is in lambda. Okay. If I define like this, then this property is satisfied, right? Because if I define like this, then f of a constant times lambda, this is basically this omega in lambda omega to the power k, and lambda to the power k comes in front. So we have lambda to the power k f of, right? But the problem is this doesn't really converge for positive k, because a, a lattice is not a bounded set. So we have, first of all, we have an unbounded set, and we are raising all the elements of the unbounded set to a positive power. Then this sum is not going to converge, right? That is why what we do is that we introduce a negative sign here. Okay. So you need to edit the definition of a homogeneous function of weight k. So we shall call a function homogeneous of weight k if f of small lambda times capital lambda is equal to small lambda to the power minus k times f of capital lambda. Like, is this definition clear to everyone? All right, so yeah, so this is the definition of a homogeneous function. All right. Yeah. So if I have two homogeneous functions of the same weight, let's say f and g, then f over g has our desired property. That is f over g of lambda times f over g of lambda times lambda is equal to f over g of lambda. Okay. So yeah, so that is why it's very natural to work with the homogeneous functions of weight k. Okay. Now, yeah. Now notice that if I have a lattice, so if lambda is a lattice that is generated by omega 1 and omega 2. So if we multiply the basis elements with, if we multiply the basis elements with a non-zero complex number, then we get a homothetic lattice, right? Then this lattice is homothetic to the lattice generated by omega 1 by omega 2, 1. Okay. And then, yeah. Also, we can, without loss of generality, we can assume that the imaginary part of omega 1 by omega 2 is positive. So without loss of generality, imaginary part of omega 1 by omega 2 is positive. Why is that? Because if we have a complex number and its imaginary part is negative, then if we take the reciprocal of it, then its imaginary part is going to be positive, right? So if omega 1 by omega 2 has imaginary part negative, then we can simply consider omega 2 by omega 1, right? So that is why we can, without loss of generality, assume that imaginary part of omega 1 by omega 2 is positive. So in other words, omega 1 by omega 2 is in the upper half plane. So omega 1 by omega 2 is in the upper half plane, and the upper half plane is defined as all the complex numbers that has imaginary part positive. So this is the set we shall be dealing with a lot. Okay. And yeah. Okay. Now, suppose I have a function f from L to C that is homogeneous of weight k. And let's say Z is a complex number in the upper half plane. Okay. Then corresponding to Z, we have a lattice. That is the lattice generated by Z and 1. Right. So let's say lambda sub z is the lattice generated by z and 1. So we can write it like this, right? So all the elements are of the form nz plus m, where n and m are integers. So this all the elements of this form. All right. Yeah. Now we can define a function from the upper half plane to the set of complex numbers. And that function takes a complex number. Sorry, it should be nz plus m, right? Thank you. Yeah. So suppose I have a homogeneous function of weight k, and let's take a complex number in the upper half plane. Then I can define a function from the upper half plane to the complex numbers that defined as f of z is equal to capital F of lambda z. Yeah. And if I have such a small f, then from the small f we can recover the capital F as well, right? Because all the lattices, so let's say if lambda is a lattice, then it is isomorphic to some lambda set, right? Not isomorphic. It is homothetic. Sorry. So if lambda is a lattice, then let's say lambda is generated by omega 1 and omega 2, and that is homothetic to omega 1 by omega 2, comma 1. And as usual, we are assuming that this ratio omega 1 by omega 2 is in the upper half plane. And this is basically equal to lambda sub omega 1 by omega 2. Okay. And if I have such a function from from the upper half plane to the complex numbers, then from that I can basically recover capital F, that is capital F of lambda is equal to capital F of omega 2 times lambda of omega 1 by omega 2. Sorry. Right. And then using the definition, I can write it as omega 2 to the power minus k, minus k, and then F of making the same mistake again. And this is equal to omega 2 to the power minus k times F of omega 1 by omega 2. So from the capital F, I can define the small f, and from the small f, I can recover capital F as well. So in order to study capital F, it's sufficient if we just study functions like this, from the upper half plane to the complex numbers. And now, it's a natural question to ask that when are two lattices equal, right? Suppose I have a lattice that is generated by omega 1 and omega 2. So suppose this is a lattice, and let's say I have another lattice, omega 1 prime and omega 2 prime. So it's a natural question to ask when these two are equal. So we have a very nice lemma here that says that this is equal if and only if so that lemma says that these two lattices are same if and only if omega 1 prime omega 2 prime is equal to omega 1 omega 2. And here I have some matrix where A, B, C, D is in GL2Z. What is GL2Z? GL2Z is the set of all the 2 times 2 matrices with integer entries that are invertible. Okay. So here A, B, C, D are integers, and AD minus BC is plus minus 1. Because if the determinant is not plus minus 1, if the determinant is some other integer, then the inverse is not in the group GL2Z, right? So that is why we need the condition that the determinant has to be either +1 or -1. So if the determinant is not +-1, let's say if the determinant is some other integer, then what is the inverse of this matrix A, B, C, D? So the inverse of A, B, C, D inverse is equal to 1 over AD minus BC, and I think it's DA minus B minus C, right? Yeah. If AD minus BC is not +-1, then the entries of this matrix are not integers. So that is why we need this condition. Okay, but what is the proof of this? Let's try to prove this. All right. Yeah. So suppose omega 1, omega. So right now we are proving this direction. So we are assuming this condition is satisfied. Then we will be then we'll prove that the two lattices are equal. So if this is satisfied, then omega 1 prime is equal to A omega 1 plus B omega 2, right? And omega 2 prime is equal to C omega 1 plus D omega 2. Okay. That means both omega 1 prime and omega 2 prime are in the lattice generated by omega 1 and omega 2. Right? And the lattice generated by omega 1 prime and omega 2 prime, so that lattice is a group. So what I mean is that Z omega 1 prime plus Z omega 2 prime, this is an additive subgroup of C, right? And this is also a group as well. So if these two elements are in this group, then the group generated by these two elements also here also. So yeah, so what I mean is that this implies that this is a subset of this. Is that clear to everyone? So yeah, so omega 1 prime and omega 2 prime are in this subgroup. So in this group generated by omega 1 and omega 2, then the subgroup omega 1 prime and omega 2 prime generates, that subgroup must also be inside this one. And we can reason similarly that then omega 1 and omega 2 is equal to the inverse of this. So I'm going to write it A, B, C, D inverse times omega 1 prime, omega 2 prime. Right? And using a similar calculation, we can show that Z omega 1 plus Z omega 2 is a subset of Z omega 1 prime plus Z omega 2 prime. Right? So then using these two, we have proved that the two lattices are equal. So if the basis elements of two lattices are related by a transformation of GL2Z, then the two lattices are the same. We are not talking about homothetic lattices here. We are talking about equal lattices. So we need to keep that in mind. Oh, we haven't proved the other direction. So if two lattices are equal, then the basis elements are related by a GL2Z transformation. So let's try to prove that. So now we are assuming that Z omega 1 plus Z omega 2 is indeed equal to Z omega 1 prime plus Z omega 2 prime, right? So if this happens, then so omega 1 is in this lattice, so it must also be in this lattice as well. So omega 1 is equal to some a omega 1 prime plus b omega 2 prime. And similarly, omega 2 is equal to c omega 1 prime plus b omega 2 prime. That is omega 1 omega 2. This is equal to a b c d omega 1 prime omega 2 prime. Right. And all the entries of this matrix are integers. And this matrix must be invertible as well, because we can go from the right hand side to the left hand side. What I mean by that is that we can write omega 1 prime and omega 2 prime as linear combinations of omega 1 and omega 2. Right? So we can write it as, let's say p omega 1 plus q omega 2, r omega 1 plus s omega 2. Yeah, and then using these two, we don't know that this matrix is invertible, right? But we need to prove that the matrix, this,
You can show that PQRS is the inverse of that.
right? So this is equal. So this basically means that omega 1 prime omega 2 prime is equal to PQRS omega 1 omega 2, right? Then omega 1 omega 2 is equal to ABCD times omega 1 prime omega 2 prime. Then this matrix is the identity matrix. So that means this PQRS matrix is the inverse of the ABCD matrix, right? And since PQRS has all the entries integer, so we can say that both of these matrices are in GL2Z. Yeah. So is this proof clear to everyone? All right. So yeah. Now we have another lemma that is related to the previous one. So what does that lemma say? The lemma says that z omega 1 plus z omega 2 is equal to z omega 1 prime plus z omega 2 prime. And no, sorry. This is in the latter part of the statement. Sorry. So suppose omega 1 by omega 2 is in the upper half plane. Then z omega 1 plus z omega 2 is equal to z omega 1 prime plus z omega 2 prime, and omega 1 prime by omega 2 prime is in the upper half plane if and only if omega 1 by omega 2 equal to omega 1 ABCD, and but this time this ABCD matrix is in SL2Z. So this is a stronger statement than the previous one. So in the previous statement, we did not require that the ratio of omega 1 and omega 2 must be in the upper half plane. But in this statement, we are requiring that the ratio has to be in the upper half plane. Okay, so one part of the proof is like really simple because, no, sorry. So we know that if the two lattices are equal, then the basis elements are related by a GL2Z transformation. Now we just have to verify that the ratio omega 1 prime by omega 2 prime is in the upper half plane if and only if the determinant of this matrix is 1. Right? So yeah. So what is the what is this element, omega 1 prime by omega 2 prime? That element is a omega 1 plus b omega 2 c omega 1 plus d omega 2, right? And this is equal to a omega 1 by omega 2 plus b c omega 1 by omega 2 plus d, right? And for simplicity, we are writing which omega 1 by omega 2 equals to z. So we know that imaginary part of z is positive. Now we are gonna see what the imaginary part of az plus b by cz plus d is. Okay, and this is equal to, if I multiply by the conjugate of the denominator, then I have cz plus d modulus square az plus b cz bar plus d. Okay. This is cz plus d. We only need the imaginary part, right? So what's the imaginary part of this thing? I think let's write it like z equals x plus iy, where x and y are the real and imaginary parts. So this is ax plus I ay. No. Sorry. So first of all, we can like multiply these two and we get a real number. So a z mod square, so ac z mod square plus bd. So this is the real part. And in the another part we get bc z bar plus adz, right? So since this is the real part, we don't need to worry about that, right? Because we are only interested in the imaginary part, right? So imaginary part of az plus b over cz plus d is equal to cz plus d mod square, the imaginary part of this one, bc z bar plus ad z bar, right? And sorry, it should be only z here. Yeah. So yeah, so cz plus d mod square is always a, yeah. So and this is equal to ad minus bc, imaginary part of z, cz plus d mod square. So we already know that the imaginary part of z is positive, right? Then the imaginary part of az plus b over cz plus d will be positive if and only if ad minus bc is positive. So imaginary part of az plus b over cz plus d is positive if and only if ad minus bc is positive. But we only have two possible values for ad minus bc, plus 1 or minus 1. So that means this is equivalent to ad minus bc equal to plus 1. Right. So we have proved that two lattices are equal and the ratio of the basis elements is in the upper half plane if and only if the basis elements of the two lattices are related by a transformation of SL to Z. Right. So yeah, so we can get an idea that the group SL to Z is of real importance for us. Yeah. And also, this motivates us to define the group action of SL to Z on the upper half plane. So now I'm going to define it. The group action, of SL2Z. So remember, a group acts on a set. So here the group is SL2Z and this acts on the upper half plane. Okay. Suppose I have a matrix A, B, C, D from SL2Z and this acts on a complex number of the upper half plane. And that gives us what? A complex number of the upper half plane. And we are defining this to be the element AZ plus B over CZ plus D. So we have already verified that if Z is in the upper half plane and ABCD is a matrix of SL2Z, then this is also in the upper half plane, right? So the group action is well defined. Now we have to verify that this is indeed a group action. So for that, we need to check two things, right? One is the identity matrix acting on a complex number is the complex number itself, and the other is some sort of a transitivity, that is gamma 1, gamma 2. This matrix acting on Z is equal to first gamma 2 acting on Z and then gamma 1 acting on that element. And here gamma 1 and gamma 2 are elements of SL2Z. Okay, checking the first one is really easy. So 1, 1, 0, 0, this acting on Z is, well, simply 1Z plus 0. So this is simply Z. So there's nothing to check. Now we are going to verify the second one. Let's say gamma 1 is ABCD and gamma 2 is EFGH. Okay. Then what is this product? This product is AE plus BG, AF plus BH, CE plus DG, CF plus DH. And this is gamma 1, this is gamma 2. Then gamma 1, sorry. The product of gamma 1 and gamma 2 acting on Z. What is this? This is this times Z plus that and the same on the denominator. So this is AE plus BGZ plus AF plus BH and then CE plus DG. This looks like CC, but this is CE. So CE plus DGZ times CF plus DH, right? So this is the left hand side. Now we have to verify that the right hand side is equal to this one as well. So what is gamma 2 acting on Z? Gamma 2 acting on Z is basically EZ plus F, GZ plus H, right? And if gamma 1 acts on this element, EZ plus F, GZ plus H, then this is simply A times this thing, EZ plus F by GZ plus H, plus B, C, this thing plus D. Okay. Let me write it for clarity. Yeah. And if we just multiply it by GZ plus H here, then we can see that these two are indeed the same. Okay. So the group action of SL2Z on the upper half plane is indeed a group action. So we have just verified that. All right. Now, yeah. Now let's get back to our homogeneous function of weight k. So let's say f from the set of lattices to the set of complex number is homogeneous of weight k. And we have seen that given such a f, we can define a function on the upper half plane, right? That is given by this. Since we have defined a group action on the upper half plane, now we can check that how the group action is related with this function. Okay, so far what have we done? We have defined homogeneous function of weight k, and to each such homogeneous function, I have a function on the upper half plane, right? And we have defined a group action on the upper half plane. Now we are gonna verify how the function behaves under the group action under the group action defined on H. that is given gamma in SL2Z, I want to check what this thing is. Okay, so this is my motivation. So now I'm going to check what this is. All right, so as usual, let's say gamma is the matrix ABCD. Okay, and then what is f of gamma z? F of gamma z is simply f of az plus b over cz plus d, right? That is how we define the group action. And this is equal to, let's say, capital F of gamma this. I'm not writing the whole expression of rational function here. So I'm just keeping it like this. Now, what is this lattice? This lattice is generated by what? This lattice is generated by two complex numbers, right? What are those two complex numbers? Exactly. So this lattice is equal to z times az plus b over cz plus d plus z, right? So that is how we define this lambda subset. Okay, and we can write it like this. This is cz plus d inverse z az plus b plus z cz plus d, right? So yeah, so this lattice gamma sub this lattice lambda sub gamma z is homothetic to this lattice that is generated by az plus b and cz plus d. Right. Then what is f of did I make a mistake here? No, I don't think so. Oh, right. Yeah. And again, since is A, B, C, D is a matrix in SL2Z, right? So this is equal to A, B, C, D, Z1. So this lattice generated by AZ plus B and CZ plus D is exactly the same as the lattice generated by Z and 1. So this is equal to CZ plus D inverse times Z plus 1. I think I need to put a parenthesis here. Sorry. So far, everything is clear to everyone? All right. Now I'm gonna let's say what is f of az plus b over cz plus d. So that is equal to f of capital F of lambda sub az plus b by cz plus d, right? And we have seen that this lattice is equal to cz plus d inverse times times this lattice, that is lambda z. Okay. Now, if we use the homogeneity condition, what do we get? What was the homogeneity condition? The homogeneity condition was that f of small lambda times capital lambda is equal to lambda to the power minus k f of capital lambda, right? So this turns out to be cz plus d to the power k, f of lambda z. And this is equal to cz plus d to the power k f of z. So that means we have proved that small f has this property. is equal to Cz plus D to the power K f of z. And this is true for all A, B, C, D in SL2Z and all Z in the complex upper half plane. Okay, and this condition is what is known as the modularity condition. Yeah. So let us revise what have we done so far. So our motivation started from. So we want to study the modular space of complex elliptic curves. Okay, and so what is the modular space of complex elliptic curve? So for that we defined what a lattice is, and then we defined what homothetic lattices are. Okay. Then we briefly said that all lattices correspond to an elliptic curve, which happens to be an abelian group. And vice versa as well. All elliptic curves, there is a lattice that generates the elliptic curve. I did not I did not define an elliptic curve rigorously. I just said that an elliptic curve is a curve of this form with some other extra condition.
It's a curve on the complex plane.
Yeah. So, well, to be more precise, it's a curve on the projective complex plane.
Right. So you did not discuss those.
No, I did not rigorously define what elliptic curves are. So these are just the motivations for the modularity condition. Okay.
Yeah, but somewhere later you put the correspondence between elliptic curves and the equivalence classes of
Yeah. So I just briefly stated the theorem. So I did not prove them. So those basically serve for the motivations for what.
Sometimes you were saying that it has the structure of an abelian group.
Right.
So how do we know how do you know that the space of elliptic curves has the structure of the abelian group?
No, the space of elliptic, so not the space of elliptic curve. So if I have an elliptic curve, so we can define a group. So we can define a group addition on it. Yeah, and under that addition, the elliptic curve forms an abelian group. So
any elliptic curve.
Yeah, any elliptic curve. So I can briefly go over what the group addition is. So let's say this is an elliptic curve. So this is the point P and this is a point Q on it. So this is P, this is Q. So if I draw the line joining P and Q, let's say this one. So this line will intersect the elliptic curve in another point. So since this curve is symmetric with respect to the x-axis, so we can reflect it with respect to the x-axis and we get this point. So this point is defined as P plus Q. So this is the group operation on the elliptic curve.
So now when you are saying that it's a modular space of elliptic curves, so you have some sort of equivalence relation here.
Yeah, so as I said, an elliptic curve is an abelian group. So by modular spaces, I mean that the equivalence classes so not equivalence classes, isomorphism classes of elliptic.
As abelian.
Yeah, as abelian groups. So yeah, so as I mentioned that all lattices correspond to an elliptic curve and vice versa. And one can prove that an elliptic curve is basically isomorphic to this quotient group. Yeah. And let's say I have two lattices, lambda 1 and lambda 1 and lambda 2, and they correspond to two elliptic curves E1 and E2. Then E1 and E2 are isomorphic as abelian groups if and only if the two lattices are homothetic. So in order to study the isomorphism classes of elliptic curves, it suffices to study the homothetic classes of the lattices. So we want to study this set, L modded out by the homothetic equivalence relation.
To understand the proof of this theorem,
Well,
you will do it later.
no, I won't be doing it later. So I'm just mentioning these facts to motivate for the modularity condition. So we want to study this set of equivalence classes of lattices under homothetic, and in order to study this set of equivalence classes, we shall be considering functions, complex valued functions. So a function that takes a lattice and spits out a complex number. And all those functions are, so all those functions naturally give rise to a function like this.
Something like two.
Yeah. And to each such capital F, we have a capital G, like this. And turns out, like finding such a function is kind of difficult. So that is why we defined homogeneous functions, because the ratio of two homogeneous functions is a function that has this property. Okay. So we define homogeneity, and we put a negative sign in front of k because the convergence issues. So yeah, so there goes the definition of a homogeneous function. Then we briefly checked so when are two lattices equal, then we got that two lattices are equal if they are related by a transformation of SL to Z. And yeah, so there's the proof, and we have defined a group action of SL to Z on H that is mainly motivated by the proof of the previous lemma. Okay, so we have defined the group action. Then we want to check that how does this function small f on the upper half plane behave under the group action. So then we got the modularity condition that this is satisfied.
Is it called conditional? It's not like theorem or
No, we are going to define modular forms right now, and one of the conditions of modular forms is exactly this one. So yeah, I guess that's enough motivation for studying modular forms. Now I'm going to define what a modular form is. Definition of a modular form. So a modular form. So of weight k is a function from the upper half plane to the complex numbers that has the following properties. So if I have a complex valued functions that takes inputs from a subset of the complex plane, ideally we want the function to be holomorphic, because holomorphic functions are the nicest possible functions, right? So we want f is holomorphic on H. The second one is the modularity condition, that is f of az plus b over cz plus d is equal to cz plus d to the power k f of z. And this has to be true for all a, b, c, d in SL to Z and Z in upper half plane. And the third one is that f of z is bounded as we go towards infinity through the imaginary axis, as imaginary part of z goes to infinity. So if a complex valued function satisfies these three conditions, we say that that function is a modular form of weight k. Here the k represents this, the exponent of cz to the cz plus d in the modularity condition.
What is called form? It's just a function.
Oh, that's a very interesting question, because like modular forms give rise to a to some sort of a differential form that is invariant under the action of SL2Z. So for instance, if I have this differential form, so this differential form is invariant under the action of SL2Z. That is, this is equal to f of gamma z d gamma z to the k. So that is why it is called a form, because that's related to the study of differential forms. So if you don't know what a differential form is, I think it's perfectly fine, because we don't need the, we won't be working with differential forms in this class. So yeah. Does anyone have any question about the definition of a modular form?
So for every element of SL to that,
Right.
it is, I'm having a whole new different functional equation,
Yeah.
and this function is satisfying all those.
Right. So we have infinitely many functional equations, right?
It's hard to believe it exists.
Exactly. So, so there's a very nice quote by, I think, Barry Mazur, who is a number theorist. So he said that. So I don't remember the exact quote. So he said that the modular forms have infinitely many symmetries. Like so many symmetries that it's hard to believe that such functions exist. But they do, and we'll see that such functions exist. Probably not today, but yeah, one of our future class for sure. Because we shall be dealing with modular forms. So if we don't know that such functions exist, so there's no point, right? So we will see examples. But yeah, there are infinitely many functional equations we have here. But well, spoiler alert. So we shall boil down these infinitely many differential equations into just two differential equations.
Because SL2 has two generic.
Exactly. So yeah. Also, one very interesting fact is that these three conditions are independent. By independent, I mean that you can have a function that satisfies two of them, but not the third one. So yeah. Also, the third condition is also very interesting, because this third condition allows us to write a modular form in a Fourier series expansion. Well, we shall see it very soon. Yeah. But yeah. So we started from the study of moduli space of complex elliptic curves, and from that we have defined modular form. Okay, and it is of no surprise that elliptic curves and modular forms are related, of course. So yeah, and the proof of Fermat's last theorem that Andrew Wiles proved. So the main gist of the proof is the equivalence of elliptic curves and modular forms. All right. Yeah, and also I think we need to mention something, that fundamentally this weight can be, so in principle this weight can be any integer. Okay, but spoilers ahead, we shall prove in this class that no modular forms of negative weight exists. So modular forms of negative weight does not exist. That needs to be proven. So we shall prove it. And yeah, and there are some active research ongoing about modular forms of half integer weights. So I don't know much about half integer weights, but yeah. So yeah, all right. Now we can examine this modularity condition for different values of ABCD. Okay, let's take let's take an element from SL to Z. For instance, let's take this one. So this is an
Because the negative k doesn't exist. Is it because the homogeneous function of like the summation like that doesn't converge?
well,
Because if it's negative,
right. So we have cheated a little bit. So we have constructed a function, and that function did not. So we have seen that that function does not convert. So that is why we said that, well, maybe we can put a negative sign on, but we haven't proved that the homogeneous functions uh, of positive weight does not exist. Right? We have not proved that. So yeah, we shall prove it very soon. Probably not today, but yeah, in future, of course. So I have that in mind. So we need to prove that, of course. All right. Yeah. Now this example. So if I take this function from if I take this matrix from SL to Z, then what is f of AZ plus B? F of AZ plus B is simply negative Z, right? And CZ plus D is negative 1. And that is equal to CZ plus D to the power K f of Z. So that means all the modular forms have this condition that f of Z is equal to negative 1 to the power K f of Z. So if f is a modular form, f must satisfy this functional equation. Now, what if k is odd? If k is odd, then what happens? Then this factor is negative 1. So f of z is minus f of z. And of course, this has to be true for all z, right? Then we get that f of z is 0. So we just use the modularity condition that f of az plus b over cz plus d equals to cz plus d to the power k f of z.
So if k is odd, then the only modular form is the zero function.
Exactly.
But also k is odd, then the modular form doesn't exist. I mean, the interesting one.
Yeah. So we have proved a very interesting theorem. So not really a theorem per se, but yeah, we have proved a very interesting result that modular forms of odd weight does not exist. Well, non-zero modular forms of odd weight does not exist. So we have proved that result. Because the constant function 0 is a modular form for every weight, right? So yeah. So only modular forms of odd weight are the constant 0 functions. Okay. Yeah. So as we discussed earlier that like if we want to check whether a function is a modular form or not, we have to check infinitely many functional equations, right? So now we shall prove a lemma that will allow us to check only finitely many conditions if if SL2Z has a finite set of generators. Okay, now lemma. So if a function f from the upper half plane to complex numbers satisfies modularity condition for gamma 1, gamma 2 in SL2Z, then it also satisfies the modularity condition for gamma 1 times gamma 2. So I'm writing modularity condition as MC. So then it also satisfies the modularity condition for gamma 1 times gamma 2 and gamma 1 inverse as well. Now let us try to prove this one. Okay. So we need to prove that f of gamma 1, gamma 2 times z. So this is the action of gamma 1 times gamma 2 on z, right? So we need to prove that this is equal to a factor of so there will be a factor and to the power k times f of z, and this factor will be if let's say these are capital C and capital D, then then capital C and capital D will be the so these two entries of the matrix gamma 1 times gamma 2. Okay. So we need to verify this thing, right? And we already know that, like we have the modularity condition for gamma 1 and gamma 2. Now let's say gamma 1 is A, B, C, D, and gamma 2 is, sorry, let's say A1, B1, C1, D1, and gamma 2 is A2, B2, C2, D2. Now suppose f of gamma 1, gamma 2 of z, and by the transitivity, so yeah, not transitivity, by the associativity of group action, this is equal to the action of gamma 1 on gamma 2 z, right? So f of gamma 1, gamma 2 z, and this is equal to f of gamma 1 of gamma 2 z. We know that f satisfies modularity condition for gamma 1. So we have that C1 gamma 2 z plus d to the power k f of gamma 2 z. So this comes from the modularity condition for gamma 1. All right. And yeah, and from the modularity condition for gamma 2, we have this is equal to C1 gamma 2 z plus d1 to the power k C2 z plus d to the power k f of z. And if we multiply now these two, so now I'm going to consider the multiplication of these two. So what is the multiplication of these two? So this is something to the power k, right? And that something is C1 A2 z plus B2 C2 z plus D2 plus D1, and we have to multiply this by C2 z plus D2. Okay. So gamma 2 z is basically this one, because that was our definition for group action. And if we carry out this multiplication, what do we get? We get that C1 A2 z plus C1 B2 plus D1 C2 z plus D1 D2. Is that right? And this, we can like rearrange this as C1 A2 plus D1 C2 of z plus C1 B2 plus D1 D2. And yeah, now we have to basically now verify that these two are indeed the elements of the second row of gamma 1 times gamma 2, right? So let us compute gamma 1 times gamma 2. So A1, B1, C1, D1, A2, B2, C2, D2. So we don't need to worry about the first row here. We just need to compute the second row. So the second row is C1, A2 plus D1, C2, right? So this is equal to this. And the last element is C1, B2 plus D1, D2. So yeah. So and what is in the first row here doesn't really matter for us right now. So we have proved that the modularity condition is satisfied for the product of gamma 1 and gamma 2. Now we just need to verify for the inverse. Okay. Let's say I have a matrix A, B, C, D in SL2Z, of course. Then what is the inverse of this matrix? That is D minus B minus CA. This one, right? And suppose we know that F satisfies the modularity condition for gamma. We now want to just show that F satisfies the modularity condition for gamma inverse. And for that purpose, we shall consider this. So F of Z is equal to F of gamma inverse Z. Right. And since F satisfies the modulative condition for gamma, then we know that this is equal to C gamma inverse Z plus D to the power K times F of gamma inverse Z. Is that right? Yeah, I think so. Then we have that F of gamma inverse Z is equal to C gamma inverse Z plus D to the power minus K F of Z. Right. Now, let us see what this thing is. So, what is gamma inverse of Z? So the bottom row of the gamma inverse was minus C and A, right? So, gamma inverse of Z is minus CZ plus A and DZ minus B. Right? And that is equal to minus CZ plus A. There is CD's, sorry, yeah, thank you. And minus CZ plus A and CDZ minus BC minus DCZ plus AD. So DCZ gets cancelled out and we get AD minus BC, which we know is 1. So that means from this we get that this is F of gamma inverse Z is equal to minus CZ plus A to the power K F of Z. So we have finally proved that if F satisfies the modularity condition for two matrices, then F satisfies the modularity condition for the product of them. Also, F satisfies the modularity condition for the inverses, right? Now we have the theorem that is, if SL2Z is generated by, let's say, a finite number of matrices, let's say gamma 1 up to gamma m, then it suffices to check the modularity condition for each gamma I. Right.
Yeah, makes sense because the product
Right. So we haven't proved that SL2Z is generated by only two elements, but we have already given it as a spoiler, but we have to prove it, right? And this theorem is clear to everyone, right? Because if SL2Z is generated by these matrices, then if I take a matrix from SL2Z, then that matrix is what? That matrix can be written as a finite string. And all the characters of the string are gamma I or gamma I inverse. Okay, and yeah, and if F satisfies the modularity condition for all the gamma i's, then F satisfies the modularity condition for their inverses as well. And yeah, and we can take the products and yeah. So it's 7:15 already, so I think we are going to stop here today, and next time we're going to start by proving that SL2Z is indeed generated by only two elements. So yeah, let me give the spoilers and call it a day for today. So the generators of SL2Z are these two matrices, 0, -1, 1, 0, this matrix and this one. So Yeah, so these two matrices generate SL2 set, which we shall prove in the next class. And I think I have two different proofs for it. One is an algebraic proof, and the other is a geometric proof. So both of them are really very beautiful and elegant proofs, and the ideas from those proofs will be needed in future as well. So yeah, I think I'm just gonna call it a day for today. Does anyone have any question? No?
Like, what is the functional equation for the second?
For this one, the functional equation is f of z plus 1 is equal to f of z.
This is just periodic function.
Yeah.
So that's why we can have like Fourier series out of the process.
Yeah. So yeah, right. So since it's periodic, we can have a Fourier series. And the functional equation for this one is, I think, isn't there a minus 1 over? Yeah, minus 1 over z equals to z to the k f of z, right? So once we have we proved that SL2Z is generated by these two elements, then we can redefine modular form as satisfying only these two functional equations. So life gets a lot easier then.
Are those like unique generator or like other pairs of?
Oh, that's a very interesting question. Suppose I denote this matrix by S and this is T. Then you can prove that SL2Z is generated by S and ST as well. Right? Because you can write T as S inverse times ST. So the generator set is not unique. All right. No more questions? All right then.